Our specific objectives are going to be considering inductive reasoning, estimation, and deductive reasoning. Let's begin with a definition of inductive reasoning. Inductive reasoning is the process of reasoning to a general conclusion through observations of specific cases. Now, inductive reasoning is actually a part of the scientific method. You know that the scientific method begins with a hypothesis, and then you do a series of experiments in order to come up with a conclusion from those data. Well, the inductive reasoning is using the results of the experiment in order to help you come up with a conclusion. Mathematically, let's look at some examples and see how we'll use inductive reasoning on them. We're going to begin by looking at something called Pascal's triangle. Now, Pascal's triangle begins with a 1. In our second row, we're going to have a 1 and a 1. In our third row, we're going to start with a 1, we're going to end with a 1, and then I'm going to put a 2 here in the middle. And then let me go ahead and write down 2 other rows. Can you determine what I'm doing in order to come up with the next row? Well, as I started drawing it, I was referring to the fact that I began each row with a 1, and I ended each row with a 1. So I'm going to do that on my next entries. The other thing is, notice that as I continue down with the rows, I'm increasing in the number of entries. So I had 1 entry, then 2, 3, 4, 5. So this row should have 6 entries. By the way I've formed it, you've noticed that as I put down the next entry, I'm always making the 2 above it end up in a situation where, like in a movie theater, you wouldn't want to have to be looking right over someone, so you're having this come in between. Well, what is the relationship between the numbers that are above and the numbers that are below? That's going to help us to fill in the next row. Notice that here, if I take the 1 and the 2 from the third row, and I want to get the entry 3 on the fourth row, I'm actually adding these 2 together. Here, if I take the 1 and the 3, I add those to get a 4. If I take the 3 and the 3, I add to get a 6. So to get the entries on the next row, inductively, we can say that we use the pattern that we saw here in order to help us determine what will come in our next row. 1 plus 4 will give us a 5. 4 plus 6 gives us 10. 6 plus 4, 10. And 4 plus 1, 5. So we think that this is going to be the next row using our logical reasoning as to what we see as the pattern that was given. As a second example, what if I give you 1 times 9 equals 9, 2 times 9 equals 18, 3 times 9 equals 27, 4 times 9 equals 36, and I'm asking you to determine the next entry by using the pattern that you notice. Well, certainly one thing you may notice about the left-hand side is that I'm increasing the number that I'm multiplying by 9. So here I'm going to have 5 times 9. On the right-hand side, if you didn't just do the multiplication, could you determine what the next entry would be by looking at the pattern? Well, notice that what's happening is the first number continues to increase. In fact, if I put a 0 in front of this 9, kind of phantomly there, you can see 0, 1, 2, 3. The next entry looks like it should be a 4. The pattern, 9, 8, 7, 6, looks like it should be a 5. Then you can see you can double check yourself. 5 times 9 does give us 45. Another way to see that is to notice that if I take the digits in the result, notice that they add up to give us a value of 9. So this product begins with 1 less than the number that I'm multiplying by, and then the second digit adds up to give us the value of 9. Now, we're also going to use inductive reasoning in order to come up with number sequences. Let's see if we can continue the patterns there. Let's start with 3, 6, 9, 12. Can we determine what the next 3 entries would be in this pattern? What we want to look at is the fact that 3 to 6 is an addition of 3. 6 to 9 is another addition of 3. 9 to 12 is another addition of 3. So noticing this pattern, we could say our next entry would be 15, and then 18, and then 21. You may also have looked at this pattern, and instead of noticing the addition of 3 each time, you might have just said, well, that's the multiples of 3. 3, 6, 9, 12, and continued in that manner. So there's more than one way to see what the next entry in the pattern is. Let's look at another one. If we have 1, 1/3, 1/9, 1/27th, and then we're trying to figure out what the next 3 entries are, what kind of pattern do you notice? Well, one thing to note is you could say, how do I get from 1 to 1/3? I could say I subtract 2/3, but that's not how I come into the next entry. Instead, what you might notice is to go from 1/3 to 1/9, you're going to multiply by 1/3. And from 1 to 1/3, you multiply by 1/3. So that may be one thing that you notice in this pattern. The other thing you may notice is that these all end up looking like fractions, except the first one, but you could write the first one as 1/1. They have a numerator of 1, and the denominator, notice, would be powers of 3. So this is 3 the first, this is 3 squared, this is 3 cubed, and then using that idea, either way, by thinking of it as a multiplication by 1/3 or by thinking of it as increasing powers of 3, you could end up getting your denominators for your next 3 entries. So you can have 1/81, and then 1/243, and then 1/729. And next, I'm going to consider a problem that doesn't have numbers in it, but it does have a pattern. We've got y, or, y, y, or, and if I put the ellipsis, that indicates that the pattern continues in that same manner. Now, what I'd like to figure out here is what is the 118th entry? Well, of course, one way to do it would be to write this out and end up going to 118, but that's going to be the long way to do it. Instead, what we want to note is that we have a pattern that recurs in groups of 3. The first in that group is going to end up giving us a y. The second in that group ends up giving us an or, and the third in that grouping ends up giving us an or. Where would 118 end up in this grouping? To figure that out, if we take 118 and we divide by 3, we can find out how many groups of 3 there are. The remainder of that division is going to be the key. For instance, if we look at the 4th entry here, in this pattern, 4 divided by 3 goes into it one time with a remainder of 1. So what we can say is that there's one full group of 3 and one left over. So that one full group of 3 is here. That's the quotient. One left over tells you that the remainder of 1 tells you the order of the next 3 that you're going to be using. Let's continue that here. 3 goes into 118. Well, 3 into 11 goes 3 times. Multiply, we get a 9. Subtracting gives us a 2. Bring down the 8. 3 into 28 goes 9 times. 9 times 3 is 27. Subtracting gives us a remainder of 1. The 39 that's here tells us the number of groups of y or r. The 1 that's left down here tells us the number of the entry in the next group that we need to pick up. In other words, we want the first entry in the next group. That would be the 118th entry. Well, the first entry is always going to end up being a y. So therefore, we can say the 118th entry in this pattern is going to give us a value of y. In order to prove that statements are true, mathematicians use something called deductive reasoning. Let's define that next. Deductive reasoning is the process of reasoning to a specific conclusion from a general statement. Let's use deductive reasoning on our next example. We want to pick a number, multiply this number by 4, add 8 to the product, divide the sum by 4, and subtract 2 from the quotient. What is going to be the relationship between the number you start with and the final number? Well, to determine this, we're going to have to try a few examples and see what happens. So, let's do that now. We're going to begin, it says pick a number, so I'm going to pick the number 5. The first thing it states for us to do is to multiply this number by 4. So, we start with the number 5. I multiply by 4, I come up with the result of 20. The next thing that it asked us to do was to add 8 to that product. So I'm going to do that here and come up with the value 28. Then we were asked to divide that sum by 4. If I take 28 and divide by 4, I come up with 7. And last, we were asked to subtract the value of 2 from that answer. And if I subtract 2 from 7, I come up with 5. So if I look at my result and compare it to my original, it appears that what happens is that we end up with the same result. Well, we could use some inductive reasoning and, as we did in our last examples, try another number. What if instead of starting with the number 5, I start with the number 7? We multiply by 4, I come up with 28. I add 8 and come up with 36. I divide by 4 and come up with 9, and then I subtract 2 from that result and come up with 7. And once more, I notice, oh look, I end up with the same thing. When we start with deductive reasoning, we don't just do a number of examples. Instead, we try to come up with a general answer. So when it says pick a number, instead of just coming up with a particular number, I'm going to start with a variable. That's going to be something that indicates any number. We want to multiply that number by 4. So what would that look like? Well, it would be 4 times n, or 4n. Let's add 8 to that. We're going to have 4n plus 8. Divide that result by 4. So we're going to have 4n plus 8, and we're going to divide that by 4. Now, let's go ahead and simplify this. If we take 4n plus 8 and divide by 4, that's the same as taking 4n, dividing it by 4, and then taking 8 and dividing it by 4. And so I'm going to rewrite this as n plus 2. Our last step is to take this result and subtract 2 from it. So that's going to be n plus 2 minus 2, which gives us back our answer of n. So we come up with the same result as we began with. And so we've just proven that no matter what number I begin with, I'll end up with the same number that I started with.